Hi, everybody. This is a makeup lecture for the second half of the Bizarre Stellar Graveyard notes. There is a video that corresponds to this that's on Canvas, but I wanted to record a fresh one because the notes have changed a little bit. I want to make sure that you get all the key terms filled in. So last week we left off right here. We were talking about black holes and how they form. Just as a reminder, this is a diagram that we can use, or really, I guess, an analogy that we can use to understand what's actually happening to space-time when a black hole forms. So imagine that this is like a rubber sheet that you can hold steady at each corner, and this sheet has the ability to sag when you put massive objects on it. If you're on the corner and you're holding on to this sheet, an object that's massive enough is going to cause the sheet to bend or to curve so much that you can no longer see down the spout from where you are on the edge, but you can tell that there's a massive object there. So when an object like a black hole curves space-time so much that even light can't make it out of this spout to reach you, we can think of this black hole as essentially a hole in the observable universe. We talked about escape velocity in Unit 1 for the first time, and we related it to how difficult it would be to get an object to go into orbit around Earth as opposed to just falling back to Earth's surface, and then opposed to going on its own trajectory, so its own path. It takes about 11 kilometers per second to escape Earth. That's approximately 25,000 miles per hour, give or take. But if you imagine that this planet on the left is like a less dense version of Earth, the more mass you try to pack into that same radius, the larger and larger escape velocity should be. Now, the turning point is when we imagine packing 3 solar masses into a small enough space that even if you replaced your rocket with just a flashlight, the light ray would end up getting bent back toward the surface. This requires an escape velocity that is up to or at least 300,000 kilometers per second, which is the speed at which light can move through a vacuum. If we were going to take Earth's radius and try to compress it down so that we can make it into a black hole, we'd have to take it all the way down from its actual radius, so approximately 6,000 kilometers or 6 million meters, and we'd have to compress it all the way down to 1 centimeter, so around the width of your pinky finger or so. And it's about that extreme mass being compacted or being forced into a very, very small volume. So once this black hole has formed, now we can think of the separation between its inside and its outside as the event horizon, so like the surface of a black hole. At that point, the escape velocity is equal to the speed of light, so that any luminous object inside of that black hole is not capable of sending any light out of it, and any new light that we send in has no way to escape. This capital R sub s is short for the Schwarzschild radius, named for Karl Schwarzschild, and it describes essentially the surface area of the event horizon. The bigger this gets, the larger the surface area gets. And something interesting happens with the mass of the black hole. It's opposite what we saw when we were talking about white dwarfs and neutron stars. The larger the black hole's mass, the larger its radius is. We know that 3 solar masses is the TOV limit, so the upper limit to how massive a neutron star can be before it's forced to evolve into something else. And that would correlate to like around 9 kilometers or so in diameter. So just a bit short of the 10-kilometer example that we used a little bit earlier in our discussion. That is not to mean that 3 solar masses is the upper limit for black holes. It just means that the larger the mass, the larger the diameter. So the smallest possible black holes that you could form would be around 9 kilometers in diameter. So if we think about what happens to this neutron star as it is being compressed downward. This is a structure that's relying completely on degeneracy pressure. So remember, this is the one that we could correlate to being sort of like a game of musical chairs, where instead of just chairs disappearing each round, you are in a progressively smaller and smaller room. There comes a tipping point where degeneracy pressure just cannot surpass or even support gravity, and the inward crush of gravity overwhelms the outward push of degeneracy pressure. So either you have a neutron star that is already too large to fall below this 3 solar mass limit, or a neutron star that's in a binary can take on additional mass and become a black hole essentially the slow way. Regardless of how the hole forms, the next step is for gravity to overcome neutron degeneracy pressure. It gets compressed down into a much, much smaller volume, and essentially the center point of the black hole, so beyond its event horizon, is a singularity. So imagine it's just one point in space. Doesn't have a height, doesn't have a width, doesn't have a depth, but it contains all the mass that's passed beyond the event horizon. Now, we know how to identify a black hole based on how it affects things that are not inside of it. The black hole's mass is going to warp space, so it would cause that rubber sheet to sag, but it would also have an effect on the flow of time. This is something that we're going to talk about more in Unit 3. But if we had an example set up where, let's say, this is you in your spaceship, you're safely far away from the event horizon of this black hole, but your lab partner is in this spaceship. They're not inside the event horizon, but they are closer to it than you are. If you had windows large enough so that you could see into your lab partner's spaceship and you could see a clock, you, from your reference frame, would think that time is going too slow for them. So, for example, something that takes 50 seconds in your spaceship, in your reference frame, might take 15 seconds in there. It's as if the clock is literally ticking more slowly. The interesting thing is that if we asked your lab partner to describe how your clock was behaving, they would come to exactly the same conclusion that you do. They would think that their clock is normal and yours is too slow. So it's about the relative positions in space-time as it relates to the depth of that spout that we can imagine forming. So let's imagine your lab partner spacecraft is inside of the spout, but still outside of the black hole. You are still going to be capable of receiving light from them, but it's going to take a different amount of time to reach you than if you were both on like flat sections of space-time. As a result, you're going to observe, let's say, a spectrum from your lab partner spaceship shift that is redshifted. So the spectral lines show up in a pattern that you recognize, but they show up in a slightly wrong portion of the spectrum. This gravitational redshift is kind of like the same type we talked about earlier in the semester. That was the result of two objects moving with a different relative velocity. So imagine you and a train that's passing you by at a crossing, or you and an ambulance that's going past you after you've already pulled over. If you are in the train or in the ambulance, there is no observed change in pitch for either of the sounds you would hear. But if you are moving at a velocity that's different than the train or the ambulance, you're going to perceive something that's like a change in pitch. So, if we're talking about black holes, we know that any material that is unlucky enough to pass through that event horizon is not retrievable. There's no way that we can maintain contact with that object, and most of its identifying traits are lost, but not all of them, which is pretty interesting. We know that the mass of an object is going to contribute to the black hole. So if I could take one solar mass of material and put it into a black hole, the black hole's mass goes up by 1. The spin or the angular momentum of that object also is still present once it passes the event horizon. So that means that the angular momentum of the object going into the event horizon is going to contribute to the angular momentum of the black hole after the fact. So it's conservation, just in a different form than what we've seen beforehand. And something we've talked very little about, but the concept of electric charge, if we had, one solar mass of negative charge and I threw it into a black hole, that would make the black hole more negative. But nothing else about the material would be identifiable anymore. So, like its color, its shape wouldn't matter. Like elasticity wouldn't matter, just mass, spin, and charge. So, if we could try to imagine how different masses distort spacetime, we find that anything that has a mass greater than 0 is going to distort spacetime. Just for low mass objects, the distortion is hard to notice. Imagine what would happen to the ping pong ball if you had it stretched out on the rubber sheet. However, progressively more massive objects are going to cause spacetime to curve in a more noticeable way. And that's how paying attention to the grid that's on this imaginary sheet can be helpful. Here we just have concentric circles. They're all the same distance away from one another, so that if we had a very, very small mass object that we could put onto that sheet, there's not much observable change. But if we take a look at our medium mass object, then it does look like the lines that are in the foreground of this image are closer together than the ones that are in the background. It's as if the actual fabric is stretching when you subject it to a high mass. And then we have our case here where our mass is something over 3 solar masses. That's the minimum that would cause a spout this deep and curvature this severe that would prevent us from being able to actually see what's down in the spout. But beyond that, if we were, sufficiently far away from this object and we didn't receive exactly the right or wrong type of nudge that would send us accelerating toward that black hole, we would be capable of orbiting it exactly the same way that we orbit the sun now, or that the moon orbits our planet. So the gravitational influence is something that we could still describe by looking to Newton's law of gravitation as an example. That was the one that told us that gravitational force is equal to the gravitational constant, capital G, times the mass of object 1 times the mass of object 2 divided by the distance between them. So it's incorrect to think about a black hole as something that just consistently pulls matter into it. That would be exactly as incorrect as imagining that the sun is just vacuuming up mass or pulling all the planets in the solar system toward it. We're able to maintain a consistent orbit around the sun just as we would be able to maintain a consistent orbit around a black hole, so long as we weren't given like an external force or an acceleration toward that hole. So here we can talk a little bit about what would happen if you visited a black hole. So let's say that we have let's make this a dummy, and the dummy is sent toward the event horizon. What we would find is that even if this were, let's say, a dummy that represents a 6-foot human, if they approach the event horizon like this, the force that the black hole exerts on the toes is going to be significantly different than what it would exert on the head of the dummy or the fingertips, which are way up here. And if you think about how this relates to Earth, that's also technically true for each one of us, but we're physically quite small compared to planet Earth. So the difference between the force at the top of our head and the force at the bottom of our feet is present, but it's not noticeable. It would be very, very noticeable for the black hole. We're talking about many solar masses of material, not just one Earth mass of material. And what we would expect to happen to this dummy is a process that I don't have written here, but it's called spaghettification. The idea is that the extreme difference between the force at the fingertips and the force at the toes would now cause our dummy to not be able to maintain its integrity or its shape. So it would get stretched out. That wouldn't actually contribute or take any mass away from the dummy, but the consequence is that now perpendicular to this line, the dummy would get squeezed in, almost as if we could take that dummy and then stretch all of it into a very, very, very long piece of spaghetti. So, up until this point, most of what we've talked about concerning black holes is kind of harping on the fact that you can't see it directly. So, you might be asking, how do we actually know that a black hole is present? The key is that it still has the ability to affect objects that are near it that can emit light to us that we can detect. So, if we can just essentially use the process of elimination along with something that's pretty familiar to us, which is Kepler's third law, we can tell whether something is orbiting a point in space or whether it is not being affected by that gravitational force. So applying Kepler's third law, we can figure out whether a black hole that's in a binary with a living star is present, or if it's not in a binary, or if it's maybe in the act of mass transfer, we can see the gas that's being pulled into the accretion disk. But it all boils down to a concept that we first encountered way back in our semester. So this image here on the left is an image that we can date back to 2019. It was the first microwave image of a black hole. We're seeing material that's surrounding the black hole. And just as we've learned beforehand, if there's like a color gradient, we know we can correlate that to a temperature gradient and then also an energy gradient. But this structure or this absence of light here that is in the center of this item is the black hole that is just interacting with material that's near it, but not inside of it. So this is in the galaxy M87, which is one that is reasonably close to a few common constellations that we can see at our latitude. Here we've got Ursa Major, and I have the Big Dipper highlighted. And then also just below it, there's the constellation Leo, the lion. This one's kind of easy to pick out because there's a shape that kind of looks like a backwards question mark. And right in this little area here, this is where you would find M87. So not something that you'd be able to see with the unaided eye, but something that you would be able to see with a like a modest telescope, because Messier was able to pick it out. And at the center of that galaxy, and we believe probably every galaxy, there's a supermassive black hole that we were able to image in microwave with the Event Horizon telescope. So, as the flowchart that we worked on in lab number 8 pinpointed, if a black hole is in a binary, then it is comparatively easy to detect because we can just watch for some object that is luminous, that we can see, that's reacting gravitationally to something we can't. And one very well-known binary between a black hole and a particularly massive large blue luminous star is in the constellation Cygnus. So this is the swan that we saw a bit earlier in this chapter. It kind of looks like a big cross in the northern sky. And in this inset here, we can see that there's clearly something that's producing light in the optical. So something that we can correlate to like ordinary matter, like this blue star. This here is just a schematic of how this blue supergiant is consistently contributing to an accretion disk, and that accretion disk is consistently producing X-rays. So this is kind of similar to the X-ray bursts we talked about on the flowchart from lab number 8. But remember, the X-ray burst is what happens when matter actually makes it all the way into the center of the accretion disk. While it is just spiraling in, it's going to produce consistent X-rays. So while this object doesn't look all that bright in the optical, it's incredibly bright in the X-ray. And the name that we can give to this is Cygnus X1. It's an X-ray source. So here's a little inset that shows what Cygnus looks like. So this is the cross shape that I was talking about. And Cygnus X1 is located right around here. So this is a perfect example of the process that we can use to try to verify whether a black hole is present before we ever try to image it, like we saw with M87. It's more or less the process of elimination. If it's not an ordinary star, and if it's too massive to be a neutron star, but we can see it interacting with other stars that are not inside of the black hole, it's likely to be a black hole. It's worth observing in microwave if possible. So this is a schematic, again, of Cygnus XR1 or Cygnus X1. Those are referring to the same item. And because this is a supergiant, it's one that is reasonably close to us. We can get a sense for how material behaves as it's moving toward the center part of this disk. And what we find is that there's an accretion disk, so hot gas that's always spiraling inward. But if we could watch like one chunk of gas or one blob that now is capable of producing an X-ray burst, what we find is there's actually a gap in that accretion disk. So that this is on the order of like 1,000 miles for this particular star. And as this blob breaks off, it's going to follow a path that looks like this yellow line. So it's destined to spiral inward, and then once it actually makes contact, that is when we would expect to see a brief but really intense increase in the X-ray, which is indicative of an X-ray burst. This here is now a different optical image of Cygnus X1. We can see a brighter star. We don't see direct evidence of the black hole in the still image, but if we could image this for a while, we would be able to tell either through spectroscopy, visual, or eclipsing binary techniques that there's something else in the system. When we image this in the radio, now everything else on the left kind of falls into the background, and instead we can focus on the jet. And we know we've seen jets a few different times in our discussion, really, really early on as stars form, and then when we talked about pulsars in lab number 9. Basically, these are a consequence of, or they're possible anytime you have rotation. So this accretion disk has material that's spiraling inward. And as a result, in the radio, this now becomes a fairly bright source. We can see an elongated jet of energy that is being ejected by that rotating black hole. Like some of the earlier examples that we saw, once you know what to look for, we find that these items are not really all that rare. They do form only from high mass stars, so they're rarer than, white dwarfs in that respect. But every galaxy is home to multiple black holes, some that are just ordinary stellar black holes, others that are like the M87 image that we just saw that are supermassive black holes. M62 is another item that's on the Messier list, so one that's relatively easy to observe with a modest telescope. And here we've got a lot of like kind of radio background emission. So think about the static that we heard in the pulsar lab last week. And then our two bright sources, where the one that's in the yellow circle here is a black hole. If we image the same region, but just in X-ray, so much shorter wavelength, much more energetic than radio waves, we can see that this black hole that was at the center of this yellow circle is not the only item that is present here. And the one that's in the red circle up here that isn't really all that prominent in X-ray, that is the neutron star. We know from experience in Lab 9 that neutron stars are more prominent. They're easier to see at radio wavelengths, so it makes sense that we can see it pretty well on the left, but when we go to X-ray, it now seems like it fades into the background. The Andromeda Galaxy provides a pretty decent opportunity because this is a large spiral galaxy like our own that is physically very, very close to us. If we are imaging that galaxy in X-ray as opposed to wide field optical, which is a larger image, so we look toward the center, there are all these little kind of purplish blobs, each one of them representing a black hole, many of them showing a lot of evidence of spiraling matter. So the kind of hazy glow that we can see surrounding some of these is something that we can tie to accretion disks. And again, these are 26 of them just in our nearest neighbor spiral galaxy. So the last bit to discuss with this chapter is the gamma ray burst. So something conceptually fairly similar to the X-ray burst, but more energetic because gamma rays have even shorter wavelengths, even higher frequencies, so they're even more energetic. When we last saw a picture of or a graph that represents an X-ray burst, we saw that it only lasted maybe for a few seconds, and that the normal or like ordinary number of X-ray or the X-ray count was not zero. So this is an object that was already bright in the X-ray, but just got temporarily much, much brighter. This is somewhat similar with the gamma ray burst, but as you notice here, if you look at the x-axis, the time frame is significantly longer. We're looking at an order of like minutes instead of just a few seconds. But just like before, we can track this back to an object that's bright in the gamma, but gets even brighter for a few minutes or so. This is a relatively newly detected item compared to some of the stuff that we talked about in the beginning of the semester, especially. We first started to detect these in the 1960s, but determining where and why they were happening wasn't something that we were able to do initially. Later observations point toward gamma rays existing in two different categories, like your ordinary gamma ray and then like a slightly more exotic type. This is an image from the 1990s that's also in the gamma ray. So that's bright object here is something that was initially very bright in gamma. But if this were a part of a video, then as we let this play, this one bright gamma object would dim over the order of a few minutes. When our ability to trace these to distant galaxies got a little bit better, we found that gamma ray bursts are somewhat rare, but not necessarily unique. Lots of distant galaxies show evidence of the same thing. So the ordinary, and I have a little asterisk here, just so that we can tell the difference between these. Ordinary gamma ray bursts are ones that we can tie to the type 2 supernova or a massive star supernova. And their light curves are going to be more like the ones that we saw in the graph a couple slides earlier, so that they stretch out over maybe days. This is an example here of an item that doesn't look like a galaxy, but it is imaged here in the gamma. So not all parts of that galaxy are equally bright in that wavelength range. We have the source of our gamma ray burst. So this is after, nearly 2 weeks after it initially began. As we take a look and go now another 2 weeks into the future, and then now a couple of months into the future, we can see that this object is dimming while the other bright objects here are not really changing much. So the host galaxy and the other bright sources are not tied to these, days or months long light curves. Instead, they are staying more or less the same. They're not changing in a really detectable way. There's some more background noise in some of these images compared to the one that we have for day 76 and 77. But aside from that, the gamma ray source itself, that's at the upper right, is the one that's changing the most. So if that's our ordinary type of gamma ray burst, what can we say about the weird gamma ray burst or the other types? These are the ones that we can correlate to really brief timescales. So they are capable of happening in any galaxy, not just ones that are very, very distant. But the evidence of this type of gamma ray burst should be easier for us to detect if we're looking at a galaxy that is nearer to us. That's just broadly true about pretty much everything we've talked about here in Unit 2. These are a little bit more unique because they require somewhat unlikely or specific events. So the birth of a black hole, so not necessarily happening at the same time as the type 2 supernova that we saw in our previous example, that is going to release gamma rays in addition to all of the other particles like neutrinos and things like that that we can look to as a warning system. If we have a galactic merger, then it becomes likely that two individual stars in those galaxies could collide. It's not a guarantee at all because neutron stars are not going to be the most common type of star in any galaxy, and you need the trajectories to be just right for these stars to collide. But two neutron stars colliding releases energy that is not going to be sustained for as long as the ordinary gamma ray burst, but it's going to be, very brief, very intense. Also, a black hole colliding with a neutron star can release gamma ray bursts that have timescales sort of like the ones that we saw previously. Now, the last thing that we can use with this information is the concept of a gravitational wave. So this is something that Einstein suggested in the early 20th century, but for the bulk of the time since then, we hadn't had the actual ability to confirm or deny. We'll talk more about this when we get into unit number 3. But the idea is that if we can model space-time as kind of being like the rubber sheet, if you could maybe walk up to that rubber sheet and flick it with your finger, you should be able to observe it oscillating for a while. But over time, that oscillation should dampen and it should go back to being essentially still. We can think of gravitational waves as being just like the waves that would oscillate along the surface of that rubber sheet, only they're traveling through space-time. And since space-time is four-dimensional, 3 spatial dimensions plus 1 temporal or time dimension, we should be able to observe like a squeeze and an extension in all 3 of our spatial dimensions. Not something that's, horribly easy to visualize, but something that we can attempt to visualize with this sequence of images. We'll let this be the inciting event that causes space-time to ripple. We can see these ripples expanding outward, and in the image that's on the right-hand side, we get a sense for how they interact with each other as they're spreading through space. There's a video here that I would encourage you to watch. It's only a few minutes long, but it's from the New York Times, and it includes a really, really nice visual representation of the type of black hole merger that is capable of producing gravitational waves like the ones that are imaged on or I guess the ones that are shown in schematic on our previous slide. And just to give a sense for what this would look like if we could watch a gamma ray burst for a very, very long amount of time, this one here is just, I believe, an exceptionally strong gamma ray burst. It started looking like this in our first image and then flared up. So it took some time for this gamma ray to go from initially giving us a heads up that it was there to reaching its greatest luminosity. But because this is something that is brief, if we wait long enough, that gamma ray source is going to go back to pretty much looking the way that it did at the beginning. Image here, so GRB 130603b is believed to be the result of a gamma ray burst that was the result of a merger of 2 compact objects. So more like the 2 neutron stars colliding or a neutron star and a black hole colliding. It is very easy to overlook the small increase in light that the wide field planetary camera from Hubble picks up. So we're looking at evidence of this gamma ray burst in the visual part of the spectrum primarily, but it is detectable. If I could take the top picture and subtract the bottom one from it, that tiny little difference in light would be something that we could determine or that we could detect. And then this was another kind of exceptionally powerful gamma ray burst. This is designated GRB 130427A, and it happened in a section of the sky that's pretty similar to or pretty close to M87, which was the source of our imaged microwave black hole. Okay, look for the link to this chapter's Kahoot on our Canvas page.